The main purpose of this screencast is to distinguish between the polarity of a bond and the polarity of a molecule, or molecular polarity, which is in the next section. So pure covalent bonding occurs when your two atoms are identical. If they are identical, there's no reason for one of the atoms to have the negative charge or the predominance of the electrons more than the other atom. They will be perfectly shared. And so pure means perfect sharing. When you do not have perfect sharing, that implies that one atom will have the negative charge more than the other atom because the electrons will be closer to it than the other atom, in which case that's going to be a polar covalent bond. We can indicate the polarity of the bond with this symbol right there. Delta, the Greek symbol you see here, can be negative or delta can be positive. In this case, the iodine has the electrical charge more than the hydrogen does in the molecule of hydrogen iodide. Iodine, of course, wants one more electron to fill up its outer shell. Hydrogen has 1 out of 2 electrons in its outer shell, and so if it gives up the electron, it becomes positive, and the iodine, when it gains an octet, becomes negative. So this would be a polar covalent bond. Super polar covalent bonds would be called ionic bonds, and that would occur when you have a metal plus a nonmetal. In this case, of course, we have a nonmetal plus a nonmetal, so we would predict not just a covalent bond, but we would predict a polar covalent bond because the two atoms are not the same. Now, the amount of the electronegativity difference between the two will be talked about in a little bit. And what electronegativity is coming up as well. You might remember that from honors chemistry. So these differences in behavior for free atoms carry over to atoms and molecules. So if we have more than 2 atoms in our molecule, we could have multiple polar covalent bonds. We could even have pure covalent bonds and polar covalent bonds within a molecule that has more than 2 atoms. So again, a polar bond is going to be a bond where you have an uneven sharing of the electrons, and one of the atoms has the electrons more than the other. Now, down here is where I talked about delta and the positive and negative. Notice there is no sharp dividing line where we can say that we've magically or mathematically gone from being covalent to being ionic, but I still think the best way to discern that, this would be an accosted by Al-Qaeda moment, that metal plus nonmetal is going to be polar covalent unless the 2 atoms are identical, in which case it's pure covalent. And I should back up. That's a metal plus a nonmetal is always going to be ionic, but a nonmetal plus nonmetal is going to be covalent. Also, you should notice in this particular page that we use this shading here to show the regions where the electrons are likely to be. And here's my way of denoting the change in electronegativity from the chart. If that change is 0, that's only because the 2 atoms are identical. If we have a change like this with a nonmetal and a nonmetal, that's definitely going to be polar covalent. If we have a significant change in chi, or electronegativity, of this amount, then it's going to be an ionic bond. I think that covers everything on that page. Now, when we come over to the next page, 372, we see a nice picture of Linus Pauling. We'll mention him a little bit, that he studied with Francis Crick of the Watson and Crick fame of the DNA structure, first elucidated back in 1953. Both Francis Crick and James Watson were, let's just say, not the nicest of people. Both of them were also pretty sarcastic towards anything having to do with God or theism. So when they were confronted with the incredible beauty of the double helix spiral, which they thought had to be true because it was so beautiful, that the only way they could explain where something like this could come to Earth or be on Earth was that it must have floated in either on asteroids or be dropped off from outer space. Those are the two hypotheses left to these two gentlemen. Once you rule out, because of your worldview, that maybe God is the one who designed the double helix of the DNA molecule. Notice that that Linus Pauling received 2 Nobel Prizes, one in chemistry and one in peace, which is pretty remarkable. So he's the one that came up with the idea of electronegativity, which isn't the same thing as electron affinity, but has the same trends. It is denoted by this Greek symbol right there, chi, and it's the measure of the ability of an atom, not to anthropomorphize atoms, that they have some type of ability, but maybe the tendency or the inclination, that also sounds funny, of an atom in a molecule to attract electrons to itself. So notice that the context of electronegativity is always within the molecule. It's never a reference to the the atom in isolation, which is going to make some important conclusions a little bit later. So let's look at these bullet points. The element with the largest electronegativity is fluorine. So obviously, if you're going from left to right on the periodic table or from bottom to top on the periodic table towards fluorine, you're going to be increasing in electronegativity. And notice that this is a sort of an artificial designation or ranking. We assign fluorine the biggest number of all, of 4, and all the other numbers then are in comparison to that. Let's look at the third bullet point. Metals typically have low values of electronegativities, which is why when you combine them with nonmetals, you have such a large electronegativity difference. And the electronegativity values for metalloids are somewhere in between the small numbers of metals and the large numbers like 4 and 3.5 and 3 for oxygen and chlorine of your nonmetals. And notice that there is a large difference in electronegativity for atoms in these trends. And we're also going to see that these are sort of average values because a lot of the electronegativity within a molecule depends upon what else is going on in that molecule as well. So here is the table of electronegativities. Here you can see chlorine with its biggest one. We come over here to cesium and rubidium and potassium with their smallest ones. And so the trends increase from bottom to top and from left to right in general. And again, we are concerned about the difference in these two numbers. So you pick any 2 atoms you want, and you find the difference between them in order to determine the electronegativity difference. Then once you have that electronegativity difference, somewhere around 0.4, it goes from being nonpolar to polar covalent. Somewhere around 1.7 or so, it begins to go from being polar covalent to extremely polar covalent, which we call ionic. So you can estimate bond polarities in a number of ways. The quick and dirty method, as I mentioned, is just to determine if you have a metal and nonmetal or if you have a nonmetal and a nonmetal. Obviously, anytime your 2 atoms are the same, your electronegativity difference will be 0. If two atoms are very close to each other, your electronegativity difference is going to be very small. The farther apart the atoms are, the bigger the electronegativity difference is going to be. Now, as far as distributing this charge about the molecule, we're going to find that in distributing the charge about the molecule, in the background, of course, is always going to be looming or lurking the ever-present and undeniable and unnegotiable, you cannot negotiate around it, the laws of thermodynamics. Stability rules the day. So when we think about charge distribution, it's important because that determines melting and boiling points, for example. It also determines other chemical properties, like how much it's going to react with an anion or cation, or I should say be attacked by it, in the sense of interacting with it, and whether you have, for example, an acid or a base. So the charge distribution is very important. And our little techniques for figuring out the charge distribution sometimes conflict with each other. And this particular polyatomic anion is a good example. This boron tetrafluoride ion, which is called tetrafluoroborate ion, tetra meaning 4, and because it's an ion, we call it the borate ion, illustrates this point. And so if you use electronegativity and if you use formal charge, you get two different answers in terms of the distribution of the negative charge. Remember what formal charge is. When we talk about a formal charge, we take what's the total number of valence electrons. For fluorine, it's 7. And then you subtract the dots, and there are 6 of them, and then you subtract the dashes. They do half the number of electrons in a dash. I just say just do the dashes, because 1 dash is 2 electrons. So if you take 7 valence electrons for fluorine and subtract 6 dots, which you can see here, and 1 dash, which you can see there, you get 0. So the formal charge of fluorine in this polyatomic anion is 0. When you look at the formal charge of boron, its total number of valence electrons is 3. You can see in this particular molecule, there are 0 dots and there are 4 dashes. So 3 minus 4 gives you your -1 formal charge. And so using formal charge, the implication is that your negative charge is somewhere around that boron, which really doesn't make any sense when you consider that fluorine is way more electronegative. So if we look at the electronegativity difference, fluorine being the most electronegative would tell us that the negative charge is going to be distributed around the outside. So I'm going to quickly erase this stuff right here and say that this negative charge is going to be located around the outside of the molecule, not in the middle of the molecule. It makes a whole lot more sense, especially since the overall anion is a negative charge. So why, again, do we select electronegativity over formal charge as the best way to show charge distribution? Well, it makes a whole lot more sense. It's much more logical. And Linus Pauling turned it into a principle. He called it the electroneutrality principle. And 2 parts to this. Number 1, electrons will be distributed in such a way that the charges are on all the atoms are as close to 0 as possible. And you can see that 0 is better than a -1 because 0 is close to 0, as close to 0 as you can get. And then second, that the negative charge is present. It should reside on the most electronegative element, which of course is fluorine. Now, if we have some resonance structures, this approach also helps us to decide which resonance structure makes the most sense. If we look at two possible resonance structures for carbon dioxide, and of course we could make a third one like this to be similar to the one right there. But the reason we would not choose either of these is because if you look at the formal charges, you get a +1 and you get a -1, whereas over here, all your formal charges are 0. So that would mean this structure right here is a better structure for representing the charge distribution around carbon dioxide than the two structures I've crossed out. And another logical reason is that this oxygen and this oxygen are the same atoms, so you would expect them to be treated, if you will, the same way by carbon. That would be a logical approach, and it's borne out by the electroneutrality principle. We can do the same thing with these three resonance structures for this particular molecule. In this particular molecule, you can see that I have a -1, a 0, and a 0 for my formal charges. Whereas over here, I have a 0, a 0, and a -1. This one right here we can rule out real quickly because we have a +1 and a -2 for formal charges. Now, adjudicating between this one and this one, again, we're going to say, well, we would expect the negative charge to be more around the most electronegative element, and oxygen is more electronegative than nitrogen. And so that's why we would go with this structure and get rid of that structure as being the best structure to represent the charge, the electron charge distribution about the molecule, or in this case, the polyatomic ion. All right, now that we've talked about bond polarity, what about molecular polarity? And this is where we talk about whether or not the entire molecule is polar. And here's a big picture idea. You can have polar bonds distributed symmetrically about a center atom, and the overall molecule will then be nonpolar. And you can have nonpolar bonds located in lots of different places in a molecule made up of many atoms, but the overall structure of the molecule is not symmetrical, and the overall molecule can be polar, even though most, if not all, of the bonds are nonpolar. So again, when we talk about molecular polarity, we're talking about symmetry. And when we're talking about bond polarity, we're talking about electronegativity. And that's the key concept. I'm going to erase all of that because I don't like my spelling there. So if we move on to the next page, how do we determine, just before I do that, I should point something out. How do we determine the molecular polarity? And the way that we determine the molecular polarity experimentally is this way. We place these molecules in an electrical field between oppositely charged plates. So if this is one metal plate, let's say it's a copper plate, and here's another metal plate, let's say it's another copper plate, and they are connected to a battery up here. If this is the negative post of the battery, and this is the positive post of the battery, so I'll make it look like a D cell or a C cell. So this is my positive post. If I turn on the switch, that means this metal pole plate is negative, and this metal plate is positive because my negative charge is flowing through the battery. It's the negative, the charge is actually the way we do it in physics. It comes out the positive and it goes to the negative. But in chemistry, you often talk about the movement of negative charge, and this is the negative post of the battery, so that makes this the negative plate. And you can see that these molecules over here are just randomly positive and negative, pointing in all kinds of different ways. Notice this new type of designation. We draw an arrow, and the point of the arrow is going to the most negative, and we represent the positive by putting a little slash through the tail of the arrow so it looks like a positive sign. And so you see that the polarity is going from the positive to the negative through the molecule. And that's sort of a designation that is consistent with physics, by the way. Physics looks at things somewhat differently than chemists do often. So now when we come over to the second picture, you will notice that all my positive sides of the molecules are attracted to the negative metal plate, and all the negative sides of each molecule, represented here in red, is attracted to the positive metal plate. And so by varying the voltage, we would have a potentiometer in here, some way of regulating the voltage. We could find that voltage that is necessary to turn all the molecules so that they align themselves in the electrical field. It might take a lot of voltage, it might take very little voltage, depending upon how polar the molecule happens to be. And that's a way of figuring out the relative polarity of all these different molecules. Now that relative polarity, or the amount of difference between the negative and positive poles, is called the dipole moment, and it's represented by the letter mu, the Greek letter M. Now there are other things in physics also represented by the letter mu, so you just got to make sure you're paying attention to the context when you see these Greek symbols being used in multiple locations in order to know what they're representing. In the case of molecules, mu represents the dipole moment, that is to say, the extent to which the molecules will line up in the electrical field. And we measure the dipole moment in a unit called the debye, which you've probably never heard of or seen, but it's certainly not in honors chemistry. And the debye is named after this guy right here, Peter Debye, and he also got a Nobel Prize in chemistry. In any case, when we use lots of different polar molecules and put them in lots of electrical fields and vary the voltage, we begin to create a way of not only determining how many debyes in the polar moment, the dipole moment. Remember, di means two poles, positive and negative. Not only do we get the magnitude of that dipole, but now we can also begin to look for trends. For example, in this group right here, we have the halogens, fluorine, chlorine, bromine, and iodine, going down the periodic table. And you can see that as you go down the periodic table, the number of debyes, or the extent of the dipole moment, gets less and less and less. And this, of course, is because as you go down the periodic table, your valence electrons on the outside are farther and farther away from the nucleus. And so the dipole moment isn't anywhere near as intense or strong. You can see a change here between oxygen going to sulfur, sulfur being below oxygen on the periodic table. Again, with that additional energy level, you're farther away from the nucleus, and your dipole moment, the number of debyes, goes down. So just for the record, this is your dipole moment symbol, and the unit of dipole is the debye, represented by the letter D. Finally, if we look at these organic compounds, methane, CH4, would have a dipole moment of 0 because it's perfectly symmetrical. It's nonpolar at all. We can make it very polar by adding one chlorine. When we add a second chlorine, it partially cancels out the polarity of the previous one, and my number of debyes goes down from 1.92 down to 1.60. And then we dilute the extreme polarity of CH3Cl even more by adding a third chlorine. But then when we add our fourth chlorine, we're back to a nonpolar molecule, and my dipole moment goes to 0. Now, one of the nice things about this edition of the book, and I suspect all other editions of this book for the years to come, is that we can represent molecules very nicely with color coding. And before we show you some of that color coding, I want to make sure I covered that page. I did. Let's wrap up a few things here. Carbon dioxide has no molecular dipole because of the fact that it's perfectly symmetrical with the carbon in the middle and a double bonded oxygen on both sides. That's a molecule that you should memorize because it's so common, and if you have to figure out its structure every time you encounter it on an AP test, it's really going to slow you down. Our interest is going to be on electron density. Where are we going to have the highest density of electrons, or the highest concentration of electrons, which of course would be at the negative pole of my polar molecule. And the greater that electron density is on one side compared to the other, the more polar the molecule and the greater the number of dibis is going to be represented by that dipole moment. And so one way to do that is with these structures right here, the ball and stick model, which is all that earlier editions of this book would show. Notice again we use the arrows pointing to the negative and the little end of the arrow being the positive. And so again, the arrow is going from the positive to the negative, which is a very common way of representing things in physics as well as chemistry. Later on in physics, when you do electrical fields and magnetic fields and you represent them by lines, they all go from the positive to the negative. But the nice thing about these pictures down here is the color coding allows us to get a better sense of the fact that these orbitals are regions of space where the electrons are going to be. And the red represents where you would have the preponderance or a higher density of electrons, and the blues would represent, by comparison, where you would have a dearth or much fewer electrons, which then by comparison would represent the positive part of the dipole, and the red would represent the negative part of the dipole. Now you'll notice in this molecule right here, boron trifluoride, that your negative parts of the molecule, you've got 3 dipoles, one there, and one there. They're evenly distributed. So this overall molecule is nonpolar, even though each of the 3 bonds is polar. When we come over to this next molecule, you can see you have a negative region here, and by comparison, this whole area here is positive, and the degree of the difference between the negative and the positive isn't as much. And so your dipole moment isn't as big as it would be, for example, as over here. Notice we have a little bit of red here. We have a lot more red here. And that's because I don't have as much of a dipole moment with this molecule. I have a greater dipole moment with that molecule. And here's a discussion that by using the colors of the rainbow, you can see the blending or the merging or the transition of going from the blue positive to the red negative, or vice versa, from the red negative to the blue positive. And this color coding, in a sense, is also a ranking of electrostatic potential measured in volts. And we'll talk about potential difference per charge a lot in AP Physics. Right, what they're showing you here, up here, is the hydrogen fluoride molecule, which is a pretty polar molecule because you've got the most electronegative element, fluorine, connected with hydrogen. Now, let's just go through this paragraph right here. regions of the molecule in which there is an attractive potential are colored red. That is, this is the region of negative charge in the molecule, and so it's going to repel other negative regions but be attracted to other positive regions of other molecules. Remember, you can have intermolecular forces as well as intramolecular forces. When we're talking about bonds within the molecule, those are intramolecular, inside the molecule. Intermolecular are between one molecule and another. And so you can have a positive polar region attracted to a negative polar region and vice versa with your polar molecules. The attraction between molecules, again, is going to be dependent upon just how strong the negative pole happens to be and just how positive the positive pole happens to be. And you can see the polarity here of tetrahedral molecules. We already went over this in the chart a little bit, going from methane, which is a nonpolar molecule, because the polar bonds are evenly distributed, so the number of dibis is 0, no net dipole moment. And then we add 1 chlorine and 2 chlorines and 3 chlorines. And pretty soon when we're back to 4, we lose all polarity again and we're back to 0 dipoles. So you can predict that a molecule, given here by some cation A and some anion X, will not be polar. I should say A being one atom and X being another atom, will not be polar regardless of whether the A or X bonds are polar if all the terminal atoms are identical. Then they're going to repel each other as far apart and be evenly distributed. Or all the X atoms or groups are arranged symmetrically. When you have perfect symmetry, you're not going to have a polar molecule, and therefore there'll be 0 dibis, which means a 0 dipole moment. And I think we're going to stop right there, and I'll pick up with bond orders, order length, and energy in the next screencast.